Okay, everybody, welcome. It is late Sunday night, the opening day of NFL football season, and it's a good time to talk about angular projectiles. To start out with, you can see from the screen we have here a picture of horizontal projectiles, and this is a little illustration. You recall last week we took a couple of tennis balls and hit them off the lab bench. And so when they were shot off, they were shot off in a horizontal direction, and you have three different balls shot at three different horizontal speeds, landing at three different spots. And what these these orange dots indicate are where the three balls are at different times. And you can see they're always at the exact same height as they move along. You know, here's time T1, say, and T2, and T3, and T4, and T5. So they're moving farther and farther away from each other in the horizontal direction, but they're always at the same height, the vertical direction at the same time. Think about horizontal projectiles, it's pretty much useless outside of outside of hitting tennis balls off a lab bench. If anybody's ever played a game of catch, all right, you think about it. Even as a little kid, you knew to throw the ball higher. You didn't throw the ball horizontally because it wouldn't get to the person, and if it did, they'd probably have to dive down to the ground to get it. Okay, so any sort of realistic projectile, you have to throw it in a somewhat horizontal and vertical direction. Okay, and that's true of anything from playing catch to throwing somebody in a racer during a quiz to anything at all. Any time in your life that you've successfully thrown a ball or caught a ball, your brain has shown you that you understand projectile motion and projectile motion shot at an angle. So let's take a look at it. Okay, for a projectile shot at an angle like this picture here, okay, there are two things that determine the time in the air. The one is the same as horizontal projectiles, it's the height. Okay, how high is the projectile off the ground when it was released? But the second thing is this vertical component of the velocity. Okay, how fast is it going in the upward direction when it's released? The faster it's going, the longer period of time it's going to be in the air. And you think about that, if you throw a ball straight up in the air very fast, it has a lot of hang time, it stays up for a long time. If you throw it not so fast, it doesn't stay in the air very long. So once again, the two things that determine height in the air is the height that it's released and the vertical component of its initial velocity. What determines the range, or the horizontal distance, is how long it's in the air, the time it's in the air, and the horizontal component of the velocity, how fast it's going in the horizontal direction. And so now what we're looking at is in this diagram, this projectile is released at this angle, and it has a horizontal component and it has a vertical component. These are initial velocity components. So if we look at a question, here's one here. A cannonball is shot at 25 meters per second at a 30-degree angle above the horizontal. If the cannon is on a 60-meter cliff, calculate the range of the cannonball. All right, so here's the cannonball, and it's shot at 25 meters per second at a 30-degree angle. So it's going both to the right and up when it's first fired. Okay? And what they want to know is how far away from the base of the cliff does it land? That's the horizontal displacement. That's what they're looking for. So if we look at the SUVAT for this problem, okay, it looks a lot like the ones for horizontal. Okay, we're looking for the horizontal, or for horizontal projectiles. You're still looking for this horizontal range, okay, and you still have the height released. I said down is negative, so I said negative 60. We still have gravity as negative 9.81 meters per second. But instead of the vertical velocity being 0, like it is with horizontal, now it's this. Okay, now it has an upward velocity, which is equal to the 25 meters per second times sine 30. Okay. The horizontal SUVAT has two variables, both of them the same. The initial horizontal velocity and the final horizontal velocity are in fact the same number. They're both this velocity, because once the cannonball is fired, there's nothing to speed it up or slow it down in this direction, in the left-right direction, except air resistance, which we're going to ignore for this. Okay, so this is the SUVAT, how it's set up. Now if I look to solve it, okay, the first thing I need to do is I need to get numbers for the horizontal initial velocity and the vertical initial velocity. So I flip it over, and you can do this. We've done this 1,000 times. Okay, all this is here. I'm just going to put the. No, I'm not going to do that apparently. Okay. Now I have my spinning ball. What we're going to do first is we're going to use trigonometry, okay, to solve for the horizontal components u, h, and uv, which turn out to be the same number. 25 times cos 30 equals 21.7 meters per second to the right. Okay, that's both the initial and final horizontal velocity, because nothing pushes the ball left or right once it's fired, because we're ignoring the air resistance. The vertical direction, uv, this is the starting velocity going up, equals 25 meters per second sine 30. Okay, if I flip it back a screen, you'll see here's uv. Okay, how fast is it going up when it's first fired? Here's UH, how fast is it going to the right when it's first fired? Right, so I solve for both of those, and then once I have that, I can solve for t using a vertical SUVAT, just like I did in the previous questions. So I plug in the numbers, and I get a quadratic equation, but you guys are whizzes with the calculator. You can graph it, you can use a quadratic formula to do whatever you do. You're going to get two answers. The first answer is 2.45 seconds before the cannonball was fired, which doesn't make a lot of sense. And the second is 5 seconds after. So 5 seconds is our time in the air. We take that 5 seconds, okay, now we know what this is. This is 5 seconds. All right, we use these three numbers to solve for t, and then we take it over here, and now we have three numbers, u in the horizontal direction, v in the horizontal direction, and t. And we use those three to solve for the horizontal displacement. So we plug in the numbers, and we get 108.7 meters per second. So don't get psyched out about it. Like I said, if you've ever thrown or caught something successfully, your brain already knows this. It already knows how to do it, and it can do it in probably 1 second. I'm going to give you 2, 3, 4, 5 minutes. So I know you can do it. But like I said, don't ever hesitate. Come in, ask some questions, and good luck. Happy NFL season, everybody.